Hello and welcome to this presentation related to the use of compound angle formulae. The formulae, as outlined on the slide, will be used to solve various problems as posed within the presentation, but please note there are no derivations of these formulae. They are used as stated on this slide. Presentation overview, briefly outline the various compound formulae we're going to consider. Then there is a brief recap of trigonometric waveforms, the sine, the cosine and the tangent form, and also a recap of sexagesimal notation, that's stated angles in terms of degrees, minutes and seconds, which are sometimes used within the solutions. The presentation initially outlines 4 examples, example 1 through to example 4 shown here. These examples show full work solutions. And here are the approximate start times related to the introduction and example 1 through to example 4. But please note these times are rounded to the nearest minute. Presentation overview continued. And then we have a series of exercises which are essentially founded on the 4 examples. This slide shows exercise 1 through to exercise 3. And again, full work solutions are shown to the exercises. And here are the approximate start times related to exercise 1 through to exercise 3. And again, these times are rounded to the nearest minute. Presentation overview continued. And this slide shows exercise 4 through to exercise 6. And again, full work solutions are shown to these exercises. Here are the approximate start times, exercise 4 through to exercise 6. And again, as always, the times are rounded to the nearest minute. And the presentation concludes with some tutorial questions for you to attempt at your own pace, commencing near the end of the presentation. Let's overview compound angle formulae. It is often advantageous to use trigonometric ratios of the sums or the differences of 2 angles. For example, electric currents can be expressed in this format, which is essentially the difference of 2 angles, or perhaps the displacement of a body can be expressed in this format here, which is a sum of 2 angles. So if angle A and angle B are any 2 angles, the sum of these, A plus B, and their difference, A minus B, are termed compound angles. And it is often convenient to express their trigonometric ratios in terms of the ratios of A and B. Introduction continued. It should be noted that the sine of A plus B does not equal to the sine of A plus the sine of B. So here are 2 calculations for you to evaluate. The first one, we have sine of, in the bracket, 30 degrees plus 45 degrees. The second sum, we have the sine of 30 degrees added to the sine of 45 degrees. If you want to type them on your calculator and evaluate these sums, you'll clearly see that the answers are different. Introduction continued. So the following formula are given without proof. Firstly, sine of A plus or minus B can be written as the sine of A multiplied by the cos of B plus or minus the cos of A multiplied by the sine of B. Label that equation 1 for reference. And if we consider the cos of A plus or minus B, that can be shown to be equal to the cos of A multiplied by the cos of B minus plus the sine of A multiplied by the sine of B. I've got that equation 2 for reference. If I now expand equation 1, accounting for the plus and the minus, I form equation 1a and equation 1b. And expanding equation 2 above, again accounting for the minus and the plus, I form equation 2a and equation 2b. Now, on inspection of the above formulae, it may be thought that an error has occurred where the signs are specified on the right hand sides on the formula cos of A plus or minus B. However, these are correct and something that we should note when applying the respective formulae. So just note in formula labelled 1 here, we have plus or minus on the left hand side and plus or minus between the terms on the right hand side. But in formula 2, we have plus or minus on the left hand side and a minus or plus on the right hand side. So just be aware of that formatting. Introduction continued. The formulae as outlined above can be used to derive the following formula related to the tangent of the sum and difference of angles. So the tan of a plus or minus b can be written as a tan of a plus or minus a tan of b, all divided by 1 minus or plus the tan of a multiplied by the tan of b. I've called that equation 3 for reference. And if we now account for the plus and the minus in the numerator, shown here and here, and the minus and the plus in the denominator, shown here and here, we can form formulae 3a and 3b for reference. So now all the above compound angle formulae are true for all values of a and b, and that can be shown by substituting the numerical values of a and b into the formulae. So that's an overview of the compound angle formulae we'll be using to solve the problems within this presentation. Introduction continued. Here's a brief recap of trigonometric waveforms. Commence initially with the sine function, y is equal to sine x, plotted here on our diagram between the range of 180 degrees, or pi radians, and negative 180 degrees, negative pi radians. And we can see that the y is equal to sine x function produces a mirror image when rotated about the origin, shown here. Imagine rotating the waveform through 180 degrees about the origin, you will form the same shape. And this characteristic is termed an odd function. In other words, sine of negative x is equal to negative sine x. Trigonometric waveforms, recap continued. Now we have the cos function, y is equal to cos x, plotted here. And we can see this produces a mirror image about the y-axis, about this axis, which is termed an even function. In other words, cos of negative x is equal to cos of x. Again, I plotted the waveform between 180 degrees and negative 180 degrees. Trigonometric waveforms, recap continued, is equal to tan x. This time I plotted between 0 and 360 degrees, or 2 pi radians. This is actually termed a discontinuous function, due to the fact the waveform approaches positive infinity and returns from negative infinity. We've reviewed in more detail the characteristics of the sine, cos and tangent waveforms in previous presentations. This slide simply shows some useful trigonometric ratios, purely for reference. So recap from a previous presentation. Just notice we can express the ratio sometimes in fractional form or in decimal form, sometimes using surd forms, shown here, and sometimes using 4 decimal places, as shown here. But so that's just purely for a reference. They're just useful trigonometric ratios to be aware of, as they can often occur within the problems we're going to consider. Here's a recap of angles in decimal and sexagesimal notation. We commonly express angles in decimal degrees, but we can also use sexagesimal notation, which is the degree, minute and second notation. Remember that in 1 degree there are 60 minutes or 3,600 seconds. So a minute is basically 1/60th of a degree, and a second is a 3,600th of a degree. You can undertake the conversions between decimal and sexagesimal notation by hand, but it's preferable to use the scientific calculator options. Here's an example of converting angles from decimal to sexagesimal notation and vice versa using the inbuilt calculator functions. Again, we reviewed this conversion in a previous presentation. Here's actually a manual calculation between decimal and sexagesimal notation. This is purely for reference. We won't be undertaking this kind of calculation within this presentation. Just a brief note related to trigonometric ratios and the scientific calculator. Usually there is a mode key or something similar that allows us to change the mode of calculation from the degree to the radian. So within the problems included in the presentation, if angles are stated in degrees, then make sure your calculator is in the degree mode. If the angles in the problems are stated in radians, then ensure your calculator is changed to the radian mode. This mode key only relates to trigonometric ratios, such as the sine, cos and the tangent functions. Let's now consider some worked examples using compound angle formulae. So here's example 1. We're asked to reduce the following expression to the cosine of one angle. So here's the expression: cos of 22 degrees multiplied by the cos of 15 degrees added to the sine of 22 degrees multiplied by the sine of 15 degrees. So using our compound angle formula, this is in the format of cos of A multiplied by the cos of B added to the sine of A multiplied by the sine of B. And that's equal to the cos of A minus B. What I'm doing here is choosing the appropriate formula from a list of compound angle formulae we considered previously. So this is the formula we'll be using. So we're using this example just to get you familiar with the format of the respective compound angle formula. So the left-hand side of the equation is as stated in the example, and that's equal to the cos of A minus the cos of B. So obviously by inspection, A is equal to 22 degrees and B is equal to 15 degrees. So reducing to the cosine of one angle is simply the cos of 22 degrees minus the 15 degrees. So it simplifies to cos of 7 degrees. So I've labelled that solution, just trying to familiarise ourselves with the format of the particular compound angle and how we denote our angles A and B in the formula. Let's consider example 2. If sine of angle M is equal to 0.53 and cos of angle N is equal to 0.2156, we're asked to determine for A, the sine of the bracket M plus N, and part B, the cos of M minus N, using compound angle formulae. So from the question, we know the sine of angle M is equal to 0.53, so to find angle M, we use the arcsine function, so arcsine of 0.53, the angle M is 32.005 degrees. Just note for reference that arcsine is the same as sine to the negative 1, the inverse sine function. And also in the question we're given the cos of angle N, 0.2156, so therefore the angle N is the inverse cos arc cos of the 0.2156, so that's 77.549 degrees. So there are two parts to example 2. Let's consider the solution to part A, shown here. So the compound angle formula we're using here is of the form sine of M plus N is equal to the sine of angle M multiplied by the cos of angle N added to the cos of angle M multiplied by the sine of angle N. Here's the compound angle formula we're using for part A. We're finding the sine ratio for the sum of two angles. So sine of the combined angles on the left hand side is equal to the sine of m, given in the question, multiplied by the cos of n, given in the question also. And that's added to the cos of 32.005 degrees, the cos of angle m, multiplied by the sine of angle n, the 77.549 degrees. Just note for reference, I'm using the dot symbol here to indicate multiplication in the formula. So I hope that's not confusing you here. I should show this multiplication symbol as a larger dot within the calculations, but hopefully you understand what I mean. So 0.53 multiplied by 0.2156 is evaluated here, and the cos of the 32.005 degrees multiplied by the sine of 77.549 degrees is evaluated here. So our final value for the sine of 109.554 degrees is 0.9423, two four significant figures. So that's part A solved. Example 2, solutions continued here. Let's now consider part B, again using the appropriate compound angle formula. Here's our solution to part B. So the appropriate compound angle formula we're using here is cos of angle M minus angle N. So we're considering the difference of two angles here. And we're given that is equal to cos of angle M multiplied by the cos of angle N. We add to that the sine of angle M multiplied by the sine of angle N. And here's the compound angle formula we're using for part B, where we're finding the cos of the difference of two angles. So now on the left hand side, that's cos of angle M minus angle N. And evaluate on the right hand side, we have cos of M multiplied by the cos of N, given in the question. And we add to that the sine of angle M, again that's given in the question, multiplied by the sine of angle N. So evaluating, we find the cos of negative 45.544 degrees is 0.7004, two four significant figures. Here's example 3. We've got to expand and simplify the following expressions. And there's 3 parts to the example, part 1, part 2, and part 3. And we've got to use compound angle formulae within these solutions. We'll show the full work solutions on the following slides. So example 3, this is part 1. We've got to expand and simplify sine of in the bracket pi plus alpha. So here's the solution to part 1. So from the expression given, we have the sine of the sum of two angles. The angles are pi and alpha. So choosing the appropriate compound angle formula, this is the formula we'll be using, labelled 1A. So in this case, angle A will be pi, angle B will be alpha. So for the right hand side of the expansion, we have sine of A, that's sine of pi, multiplied by cos of B, cos alpha. And we add to that the cos of A, cos of pi, multiplied by the sine of B, the sine of alpha. Now just note from our graph shown previously, the sine of angle pi is actually 0. And referring to the sine wave we've shown previously, the angle pi radians or 180 degrees, we would read off 0 on the vertical axis. And when the angle is pi radians, cos of pi is negative 1. So for our cosine waveform shown here, for an angle of pi or 180 degrees here on the horizontal axis, we read off a ratio of negative 1 on the vertical axis. So therefore inserting the numerical value, sine of pi is 0, multiplied by cos of alpha, so we lose this term, and then cos of pi is negative 1, multiplied by the sine of alpha. So simplifying then, the sine of pi plus alpha, using the compound angle formula, can be shown to be negative sine alpha. Here's example 3. This time we're considering part 2. We've got to simplify negative cos in the bracket 90 degrees plus beta. Here's our solution to part 2. So negative cos 90 degrees plus beta. Here's the compound angle formula we're going to use. The cosine of the sum of two angles. So here's the formula we'll be using. Labelled as 2a on our listing here. So cos of a plus b. In this case, a is 90 degrees and b is beta. So notice here the negative is kept outside of the cos function, as stated in the original question. So on the right hand side we have cos of a, that's cos of 90 degrees, multiplied by cos of b, that's cos of beta. Then we minus the sine of a, sine of 90 degrees, which is multiplied by the sine of b, sine of beta. If we now consider our trig waveforms, sine of 90 degrees has a ratio of 1. We can see here sine of 90 degrees, or pi upon 2 radians, has a ratio of 1. And the cos of 90 degrees has a ratio of 0. Which we can see from this diagram. At 90 degrees on the horizontal axis, the curve crosses the horizontal axis, so the ratio is 0. So inserting the numerical values into the right hand side of the compound angle formula, we know the cos of 90 degrees is 0. So again this term becomes 0. And the sine of 90 degrees is 1, which is multiplied by the sine of beta. So negative cos 90 degrees plus beta simplifies to sine beta. Notice the double negative effect here produces a positive sine beta. So example 3 and part 3, we've got to simplify sine of in bracket a minus b minus sine of a plus b. So this time we'll be using two compound angle formulae, one for the sine of the difference of two angles and subtracting from that the sine of the sum of two angles. So here are the two compound angle formulae we're going to use on this slide. So here's the sine of the difference of two angles expanded. Here's the sine of the sum of two angles expanded. Just notice the change of sign occurs here because there's a negative outside of the bracket here. So now we can see that this term cancels with this term to leave us with these two terms here and here. Thus we simplify the given expression to negative 2 cos of a multiplied by sine of b. Here's example 4. Making use of compound angle formulae, we have to solve the equation 6 multiplied by the sine of in bracket theta plus 30 degrees is equal to 19 cos of theta. We have to solve for values between 0 degrees and 360 degrees only. Obviously there are an infinite number of solutions here, so we're limiting the solutions that occur between 0 and 360 degrees. The full work solution is shown on the following slides. Example 4, here's the solution. So the compound angle formula we use relates to the sine, the sum of two angles. So this formula here, sine of angle A plus angle B. And here's the expansion on the right hand side. So in this case, A is theta, B is 30 degrees. Notice the 6 is multiplying the sine function, so on the right hand side the 6 is outside of the compound angle expression here. And inside the square bracket we have sine of theta multiplied by cos of 30 degrees, and then cos of theta multiplied by sine of 30 degrees. So next line, here's the cos of 30 degrees multiplied by sine of theta. Notice I'm using decimals here for my ratio of cos of 30. Then we have the sine of 30, which is 0.5 multiplied by the cos of theta. On the next line, simply factored by the 6 to produce these terms shown here. But we note for initial problem posed that 6 sine of theta plus 30 degrees is equal to 19 cos of theta, shown here. So we can equate 19 cos theta to this expression here. Example 4, solution continued. Just repeated this line for convenience. Now we have an equation, but it contains both sine and cos terms, which is difficult to solve here. So we're going to try and simplify the expression in terms of one trig function, the tan function. To do that, we're simply going to divide throughout by cos of theta. So on the next line, that's exactly what I'm doing. Every term is divided by cos theta. On the left-hand side, the cos theta in the numerator cancels with cos theta in the denominator. Becomes 1. 1 times 19 is 19. On the left-hand side here. And on the right-hand side, this first term here, we have sine of theta divided by cos of theta. And we know from our previous work, tan theta is defined as sine theta divided by cos theta. So here's tan theta on the next line. And for this term, the cos theta divided by cos theta again becomes 1. So 1 times 3 is 3, so plus 3 on the right-hand side. So there's the right-hand side expression. On the next line, I simply subtract 3 from both sides of the equation, and I divide throughout by 5.196. So we can see that theta is equal to the arctan, the inverse tan, of 3.08 in this case. Now there are an infinite number of solutions because the tangent waveform is periodic, continues forever, but the question wants us to limit our solutions between 0 and 360 degrees. So from the inverse tangent function, our calculator states a value of 72 degrees, but don't forget there are always two solutions between 0 and 360 degrees. Here's a plot of the tangent waveform. So for the tangent ratio of 3.08, our first solution is 72 degrees. That's a solution in our first quadrant, but we'll also have a solution in our third quadrant of 252 degrees. And for recap, the two angles can be determined with reference to the ASTC diagram, which we reviewed in a previous presentation, where in the first quadrant, all the trig functions are positive ratio. In the second quadrant, only the sine function is positive ratio. Third quadrant, only the tan function is positive ratio. And in the fourth quadrant, only the cosine function has a positive ratio. So as our tangent ratio is positive 3.08, our solutions occur in the first quadrant and in the third quadrant. So our second solution for theta. We'll now consider some tutorial exercises for you to attempt. These exercises are essentially based on the previous examples. So exercise 1, we're asked to show that cos of y minus pi in the bracket added to sine of y plus pi upon 2 in the bracket is equal to 0. I encourage you to stop the presentation and attempt exercise 1. As a hint, here are the two compound angle formulae we'll be using, labelled 1a and 2b on our slide here. But I will show you the full work solution on the following slides. So exercise 1, commencement of the solution. So our initial compound angle formula we're going to use relates to this part of the equation, the cos of y minus pi in the bracket. So we have cos, so A in this case will be angle y, and B in this case will be angle pi. I just now insert the values of A and B into the right hand side of the formula. So we have cos of A is cos of y, multiplied by the cos of B, cos of pi. And we add to that the sine of A, sine of y, multiplied by the sine of B, sine of pi. With reference to our cosine waveform, the cos of pi, cos at 180 degrees, is actually -1. and the sine of pi, sine of 180 degrees, is 0. Here's the cosine waveform showing it angle pi. We have -1 on our ratio for the cosine waveform, and for the sine waveform at angle pi we have a 0 ratio. So our solution for the cos of the difference in angles here is negative cos of y. That's part A, as I've labelled this part of the solution. Exercise 1, solution continued. Just repeated the answer from the previous slide for reference. Next compound angle formula we'll consider is the sine of angle A plus B. In this case, angle A is y, angle B is pi upon 2. So then simply inserting A and B into the right hand side of our formula here. And notice that cos of pi upon 2 is 0. Then we will lose this part of the equation. And sine of pi upon 2 is 1. So we can see in this case the answer is cos y. So back to our original problem, we can now show that the left hand side is equal to the right hand side, which is equal to 0. So we've answered exercise 1. Exercise 2, this time we're asked to prove that tan of x plus pi upon 4 in the bracket multiplied by tan of x minus pi upon 4 in the bracket is equal to -1. Again, as a hint, we'll be using compound angle formulae labelled 3a and 3b here. And again, I would encourage you to stop the presentation and attempt exercise 2, but the full work solution is shown on the following slides. Exercise 2, here's the commencement of the solution. First of all, we'll consider this part of the problem. That's the form tan of a plus b. This is our compound angle formula. In this case, the a is equal to x and the b is equal to pi upon 4. You work through the solution at your own pace. The final equation. For the first part of the solution, I've labelled that as a here. Just note here that tan of pi upon 4, or tan of 45 degrees, is 1. So that's how we end up with tan x plus 1 on the top line and the 1 minus tan x on the bottom line. Here's our tangent waveform plotted, essentially at 45 degrees, which is about here on our diagram. That would produce a ratio of 1. That was one of the useful trig ratios we highlighted on our previous slide. The ratio of tan 45 degrees, or tan pi upon 4, is 1. Exercise 2, solution continued. Consider this part of the problem. I'm using this compound angle formula. And again, a is equal to x, and b is equal to pi upon 4. Placing the a and the b into the formula is our answer for the tan of x minus pi upon 4. Again, notice the ratio of tan pi upon 4 is 1. So we end up with a solution here for part B of our problem. Exercise 2, solution continued. So now we can replace the tan of x plus pi upon 4 with this expression, and the tan of x minus pi upon 4 with this expression. Note that the numerator here cancels with the denominator here, hence the 1 shown here and the 1 shown here. So our expression simplifies to this. All that's happened on the next line, I'm trying to make the numerator the same as the denominator. So I've taken a negative outside of this bracket and I've changed the sign of the terms inside the bracket. We have inside the bracket 1 minus tan x The denominator we have 1 minus tan x. This expression in the numerator cancels the expression in the denominator to give us the value of 1. And then we can clearly show that the answer is negative 1. So we have again solved the problem posed. Here's exercise 3. Given in the question sine of p and cos of q. And we're asked to determine in part A, sine of p minus q, part B, cos of p plus q, and part C, tan of p plus q. Answers shown in the square bracket here. I'd encourage you to stop the presentation and attempt exercise 3, but the full work solution is shown on the following slides. So exercise 3, here's the solution to part A. I'll let you review this at your own pace. Solution is quite similar to that of example 2. Exercise 3, solution continued here. Solution for part B. Again, I'll let you review this at your own pace. Answer shown here. And exercise 3, solution continued. This is part C. Again, I'll let you review the solution at your own pace. The answer is shown here. Exercise 4. We're asked to solve the equation shown here for values between 0 and 360 degrees. The answer is shown here in the bracket. This solution is very much like that for example 4 we reviewed previously. I'd encourage you to stop the presentation and attempt exercise 4, but the full work solution is shown on the following slide. So exercise 4, here's the full solution. Just note within the solution from this line here to this line here, we're dividing throughout by cos of x. Again, if you refer to example 4, you'll see the technique used here. Remember also when evaluating the inverse tangent function, there are always two solutions between 0 and 360 degrees. Here's exercise 4, solution continued. This shows the plot of the tangent curve, and it shows for our ratio of 1.694, we can find our two solutions, one here and one here. Again, these solutions can be found using the ASTC diagram we outlined previously. Here's exercise 5. Again, similar to example 2 we reviewed previously. We're given cos x is 0.15, sine of y is 0.84. Using compound angle theory, we have to evaluate part A, sine of x minus y, part B, cos of x minus y, and part C, tan of x plus y. Answer is shown in the bracket here. I'd encourage you to stop the presentation and attempt exercise 5, but full work solutions are shown on the following slides. So exercise 5, here's the solution for part A, shown here. Answer to 4 decimal places, shown here. Exercise 5, continued. Here's the solution for part B. Answer is shown here. And exercise 5, solution continued. This is for part C, shown here. Answer shown here. I have labelled the solution to show you the calculations in detail, purely for reference there. And exercise 6, we've got to reduce the following expressions to the sine or the cosine of one angle. And for ease of reference, here is the original slide we used showing the various compound angle formulae related to sine and cosine functions. You have to choose which is the appropriate formula to use within the various parts of the problem. So again, I'd encourage you to start the presentation and attempt exercise 6. Answers for part A is shown here. Answer for part B is shown here. Full work solutions are shown on the following slides. Exercise 6 solutions is part A. I'll let you review the solution at your own pace. This is the compound angle formula used. Here's the final answer. And exercise 6 solution continued is part B, the compound angle formula used, and again the final answer. And finally, I'll leave you with some tutorial questions to attempt at your own time. Here's question 1 and question 2. Answers are shown in the square bracket. Here's question 3 and question 4. In question 3, we have to show that. We have two equations here to effectively be proved. And the same with question 4, we have to prove the two equations stated. Here's question 5 and question 6. Answers shown in the square brackets. Notice the answers to question 6 are shown in degrees and minutes. Here's the bibliography. A very good engineering textbook, particularly for technician engineering students. And I hope this presentation has been of some use to you. And as always, thank you for viewing.